Here we have a wood beam that is supported by two ropes that are tied at the center of mass of the wood beam. We want to find the tension carried by each rope. In this case, we're told that this beam is supported by the two ropes. That implies that it is hanging there, it is suspended, and it's not moving. So we can conclude from that this system must be in static equilibrium. So our process here is to sum up the forces acting on the object, and we know that the sum of those forces must be zero because the object is in static equilibrium. If we look at the goal of this problem, we're supposed to find the tension carried by each rope. A tension is a type of force, so if we are pursuing finding the different forces acting in the system, we would expect to find the tensions there. Our process here, if we are treating this beam as a particle, we have the forces that where the ropes are tied is at the center of mass, so basically we can treat this beam as if it's a particle. There's its center of mass. We can do a force identification. We have 2 points of contact here, so we're going to have a tension associated with one of them, a tension associated with the other. These are two different ropes, so we'll have two different tensions there. There's no other points of contact, but the beam has a weight to it. And so essentially what we'll do here is draw our free body diagram. Here are our axes, and here's our particle representing the beam with the forces acting on it. We're going to pursue this the way that we normally would. We're going to break our forces into components: T1y, T1x, T2y, T2x, and we're going to turn the two tension vectors into x and y components. And then we're going to apply Newton's second law, just like we've done before. We break our Newton's second law up into x and y components, since each component is separate. The only difference is that we have our null vector here, which means that all the forces add up to be zero everywhere, so that our acceleration ends up being zero in this case, as we are in static equilibrium. The forces that I have in the x direction here, I have T1x is pointing to the, or I should say, T1x is pointing to the left. There should be a T1x here. I've got a T2x that's pointing to the right, so that's going to be positive. That's this one here. And those are the only two forces in the horizontal direction, so together those must equal zero. Looking in the y direction, I've got T1y is pulling up. I've got T2y is also pulling up. I've got the weight that's pulling down, and together those have to equal zero also. Our next step is to break these up into terms of the magnitude and direction. Right now I've got 4 different unknown values, but I really don't. T1x and T1y aren't just two random values, but rather they are the two components of the same T1 vector. So my T1x is opposite that 20-degree angle. My T1y is adjacent to that 20-degree angle. And so I can simplify the way that T1x and T1y are expressed in terms of the magnitude of that tension T1 and sines and cosines. I can do the same thing with T2x and T2y. I have the angle associated with T2. I also have the weight. The weight is often mg, but in this case I'm given 50 newtons. And newtons is already a measure of force, so my weight here is already 50 newtons. And what I have here is basically sine and cosine of 20 or 30 degrees. Those are all fixed values that come out of your calculator. It's not something you know off the top of your head, but your calculator knows it. So we have numbers here, a number there. What we don't have is T1 or T2, so we have 2 equations and 2 unknowns that we're going to solve. So the way we're going to do that is to solve for one of our variables in one equation and plug it into the other equation. This is the simpler equation, so I'm going to attack that one first. I'm going to add this term across the equal sign. It's negative over here, so it will become positive when I move it across the equal sign. Now I have these two terms. I'm going to divide both sides by sine of 20 to solve for t1. Notice that these are two separate values. You can't cancel anything. You can't cancel 30 over 20. You can't cancel signs. These are two independent numbers. But we have solved for t1. I'm going to take this expression for t1, and I'm going to substitute this in for t1 in the second equation. Here I've subbed in, where this term right here is just the t1 that we had before. Everything else is the same. I'm going to add 50 to both sides to cancel that out. Move the 50 across the equal sign there. And then what you'll notice on this side, this is a number. This is complicated, but it's just a number. I have a common factor of t2 that I can factor out. This whole thing is just some number. Your calculator will tell you what it is. And what we'll do here is say that we have 2.2398 t2 is equal to 50, and then t2 must be equal to 22.324. This is a tension. Tension is measured in newtons. It's a type of force. In this case, we've got 2 sig figs there, let's say, so we'll round this to 2 sig figs also. But we want the full number so that we are not allowing rounding errors to propagate through our calculation. We want to hold on to more sig figs, and we can round at the end. We're not quite done yet. We found the tension in rope 2. Now we need to find the tension in rope 1. We have this expression relating T1 and T2. And so what we can do here, now that we know what T2 is, we can use a bigger value with more decimal places, and we'll go ahead and multiply out and find T1. Here I have T1. I'm going to round it to sig figs also. Notice in this case, we have two different ropes supporting this beam. The total weight of the beam is 50 newtons. The total supporting weight is about 55 newtons there. Almost 56 based on how much we rounded. So what's happening here is that both ropes are supporting the weight of the beam, but because they're pulling at these angles, they're pulling up to support the weight of the beam. They're also pulling to the side, pulling against each other. And so the fact that the total force from the ropes is greater than the total weight of the beam shows the sort of inefficiency of the system. But what you'll see as well is that having the rope split up like this will also give stability to the system. So there's a trade-off that you'll have to make there.